Hello guys. After flying over 32 hours, being squeezed in a tiny airplane seat, it's a pleasure for me to being able to stand up in front of you and talk about a topic that I really enjoy, after wine, of course, that is Web3 security. So let me introduce myself. My name is Quispe Gonzales. I work at Halborn, a company specialized in Web3 security. I have been hacking for around 13 years, different technologies, web, mobile, ATM, Swift, you name it. And the last 4 of them focusing on Web3 security. So right now I'm working with DeFi projects, cryptography, layer 1, layer 2, a solution, etc. Off the record, I'm a wine lover, so if you enjoy this talk, you can invite me a glass of wine or a bottle, you decide. So today we are going to see 2 things mainly. The first one is how a Rust-based blockchain works, and the second one is some very interesting vulnerabilities my team and me have found over this time. Okay, before starting this intro, would like to know how many of you are Web3 security researchers or are dedicated to security? Please raise your hand. Oh, a lot. So, and from you, how many of you have audited before a blockchain? Oh, a lot of expertise in the room, cool. So what happens? Most of the Web3 security auditors are used to audit smart contracts, most of the time. But what happens when appears a blockchain? And many words comes to our mind: validator, full node, consensus, execution, VM. So how to hack this kind of technology? Every time something new comes to my home, so I remember this anonymous philosopher on Twitter. If I'm building a house, I would spend half of the time looking at YouTube videos. And to be honest, sadly, there are not YouTube videos on how to hack a blockchain. Maybe soon. So first, we are going to understand how a blockchain works through a transaction lifecycle. You know that in security, we most of the time use very common names like Alice and Bob, right? But we are going to change that. This is old school. Let me introduce you Ayesa. Actually, Ayesa is a real person. She's here among us. If you find her, say hello to her. She doesn't buy anymore. Okay, so Ayesa loves money, and she is a very smart investor. So she decided to add his coin to pool liquidity. So what she thinks is that after some time passes, she will be able to claim some reward. And the time passes, and she tries to claim the reward. What happened behind scenes? So first, we have Ayesa with his client, in this case, a wallet, and the wallet tries to build a transaction. Let's name it transaction 14. Why 14? Because before that transaction, she executed 13 transactions successfully. So if we take a closer look to transaction 14, we are going to see a raw data, we are going to see a public key, and a signature. Obviously, the signature is so nobody can impersonate her. If we take a closer look at the raw data, we are going to see different fields like Ayesa's address, we're going to see the payload, so basically what she wants to try to carry out. We're going to see some gas-related data, etc. And now, the client, I mean the wallet, send a transaction to a full node. Here comes a new actor, full node. So to understand full node, it's the typical name it received from different blockchains. In some specific one, like Casper, for example, the name is non-validator node, and so on. But what a full node does? Basically, this full node needs to have a copy of the blockchain inside it. Could be a full copy or could be a prune version of the blockchain. And number 2, any one of us can run a full node. We just need a computer and we can have a copy of the blockchain there. Then we also have a component called mempool. So mempool basically is a temporary storage. Could be in memory, could be on disk, but the idea is that in this mempool, all the unconfirmed transactions wait until they are confirmed in a later phase. Something to say here is before a transaction is added to the mempool, there are some basic checks that need to be met. For example, syntax, for example, balance, fee check, etc. OK, we have a full node with a mempool. Now, you have to know that a full node also works as a relayer, and it sends information to a validator. Very interesting here, a validator also has its own copy of the blockchain. And as the name suggests, validators validates and adds blocks to the blockchain. Important to know that not everyone can be a validator. You need to invest a lot of coins. You need to stake that coins. And if you do things correctly, you're going to earn some rewards. But if you don't do it, your stake coins are going to be slashed. Obviously, validator has its own mempool. So again, full node sends a transaction to the validator. Validator adds the transaction to its own mempool. Now, what happens? This architecture is very common in many of the blockchain, but some blockchain, for example, Aptos, have a different schema. Full node doesn't communicate directly to the validator, but sends a transaction to a validator full node, and this validator full node sends a transaction to the validator at the end. So it varies a little, but at the end, the information comes from full node to validator. So what else? Here, important to understand. One of the validators received the transaction, but not all of them. So using a sharing mempool protocol, validator one, the one who received the transaction, send the transaction and exchange the transaction with other validators. So at the end, transaction 14, remember transaction 14, is in the mempool of all the validators participating in this blockchain. Now, time for a new component called consensus. So consensus, every blockchain has its own version of consensus. For example, Aptos has Aptos BFT and so on. What happens with consensus? In every round, the validators need to decide who's going to be the leader in that round. So they agree in which one of them is going to be the leader, and the leader will be selected with different criteria depending on the consensus mechanism that it applies. Something interesting, the leader is going to change every round. Again, will depend on the consensus mechanism. So now let's imagine that the leader is validator X. So validator X is going to take the transactions that are in its own mempool and will coordinate with other validators to understand what is the order of the transactions in a block. And this point is very important. Why? Because at the end, order matters. It's like attending a conference. It's not the same that you, in a typical scenario, you buy the ticket and then you attend the conference. Vice versa doesn't work. You cannot attend a conference and then after saying goodbye, paying the ticket. So it's the same for the transactions. Now, after consensus component, each one of the validators, remember that at this point, each one of the validators have some transactions and they will try to execute those transactions. So let's see at validator X, the information goes from consensus to execution layer. And this layer execution is going to make a transaction ordering. But wait, Luis, didn't you say that consensus also ordered the transaction? Why execution is ordering again? Good question, Luis. What happens is that execution layer is going to respect consensus order. However, it will try to apply some optimization. For example, if two transactions are going to affect different resources, they can, for example, execute in parallel. Also important to mention that execution layer is going to be the orchestrator. Who is going to be the slave is going to be the virtual machine layer. Virtual machine layer is going to actually execute the code. I mean, run the bytecode from the smart contracts. Also, it's going to apply some rules, for example, ownership. And also, and very important, this part is very important, it will update the blockchain in a simulated way. At this point, no blockchain has been updated. It's a simulation. Remember that word, simulation. Obviously, depending on the blockchain, we will have different virtual machine layer. For example, Aptos use Move VM, Quispe use WebAssembly VM, and so on. Now, virtual machine will give the results to the execution. An execution will append transactions in a Merkle tree. We have seen a lot of time, we have heard about different times about Merkle tree. How it works? Well, each one of the blockchain have its own version of Merkle tree, but let's see a simple example. So imagine that this transaction A until transaction E, are the successful transaction of this block. So we are going to have a hash for each one of the transactions. We are going to take every pair of hash, we are going to concatenate them, and we are going to create new hashes, and so on, until we reach the last that is called Merkle root. This Merkle root is going to be added to the header of the block. This is, in general, a Merkle tree. Now, after generating the Merkle tree for the block header, you can wonder, why do you need that hash? It's a way to find very easy if a transaction was present in a block or not. But after that, and here very important, the validator is going to generate a new hash called root hash. You remember that some moments ago I mentioned a simulation, a draft blockchain. Okay, that draft blockchain, this execution layer are going to generate a root hash or hashes. And it will depend, because if we talk, for example, about Aptos, Aptos will generate only one root hash. On the other hand, for example, Quispe will generate one root hash for each shard. Shard basically is a slide of a blockchain. Sui also will generate root hashes for each resource that is affected. So at the end, once the execution layer generates those root hashes, send information, and it's going to be using different Merkle tree, and it's going to send that information to consensus layer. And consensus layer are going to talk with other consensus in other validators to understand if after each validator have executed its own transaction, they reach to the same root hashes, root hash or root hashes. If that's the case, consensus sends a signal to execution layer, and execution updates the blockchain state. Some moments ago, we are talking about a draft, a simulation, and now we are talking about a real modification of the blockchain state. And finally, it's going to be stored permanently in the storage layer. That's how it works. Now, that's everything that happens behind scenes. And finally, you can see that Ayesa, now he has 25 coins after claiming her reward, and those coins are reduced from the contract. Very easy. That's the happy part. Now, let's see from security perspective. What happens? Ayesa can be malicious. Her client can be malicious. The full node, remember, any one of us can run a full node, can also be malicious. Also, some validators can be malicious. So the last frontier to protect the security of a blockchain relies on protecting the security of the different components of a validator. So let's see. So I'm going to show you some real-world vulnerabilities we have found. The first one of them, by the way, a caution of war. All these vulnerabilities have been found in real-life projects. All of them have already been patched, so they don't apply anymore, just in case you want to know. The first one is related to the project called Sui, and the component affected is the execution layer, and how we found it? Through manual review. So talking about this, you know that every time you send a transaction, you have to pay a fee. Could be a fee for computation, could be a fee for storage, and so on. So what happened? And most of the time in this kind of blockchain, consensus validators reach to a consensus about what is going to be the fee for storage and for computation. So in theory, nobody other than the validators can change those parameters. Actually, if we see the code, we see that we have different kinds of transactions, and one of them is called change epoch, and it's a system transaction. So nobody else, any external party, is supposed to call this transaction. And if we see the function on how to verify the transaction, we are going to see that the verify function calls another one called addSender blah 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 function. If we take a closer look to that function, we are going to see that here we have a verification. If the transaction has already been verified, just continue. Don't do anything. Not make sense. But if the transaction is a system transaction, also don't do anything. Just continue. So if we take a closer look about is system transaction function that you see here, we are going to see that this function verifies. This transaction is change epoch, yes or no? If it's yes, don't do anything. So apparently, we cannot bypass that, or can we? So if we see the definition of the transaction, we are going to see that there are two kinds of transactions. One of them is a single transaction, a classical transaction, and the other one is a batch transaction. So basically, in a batch transaction, we create a vector of single transaction, and we can send it. So how to attack it? Very easy. We create a single transaction, and we put that transaction inside a vector, and we create a batch transaction with only one transaction with change epoch. And we apply it, and as a result, we are going to successfully execute that transaction to change the epoch. Very easy. We can, for example, put a 0 fee for storage and 0 fee for computation. So free transaction for everyone. The second attack applies to a Rust-based rollup, and this is regarding the gas fees. So what happened? In this case, we have that the affected component is mempool, and also we have found this vulnerability through manual review. So if we see here in the submit transaction, this function adds a transaction to a mempool. But before adding to a mempool, do some verification. So for example, it verifies if the sequence numbers, the number I mentioned some moments ago, transaction 14, remember, that's the sequence number. If the sequence number is less than the current sequence number, so through an error message. In this case, the error message is sequence number to all. Why does it happen? Because mempool is the first frontier. We don't want to use resources from the validator unless we have validated something else in the mempool. However, in this validation, we don't see anything about higher number sequences. So if, for example, right now, the sequence number is 10, what happens if I create a transaction with a sequence number 11, 12, 100, 1000? At some point, it makes sense that the sequence number is higher than the current one, but not too much. So what is going to happen? Let's see. Here we have a test when we have two kinds of transactions that are invalid. The first one, I'm going to try to transfer more coins from Alice to someone else. Because we are trying to transfer more coins than she has, the transaction is going to fail. And as expected, even if a transaction fails, it's going to cost you some fees, right? That's the expected behavior. In the second scenario, we are going to send 1,000 transactions using a high sequence number. Is it going to cost to the attacker any fee or not? So in the first scenario, you can see that the initial balance is 100,000 after sending only one transaction. When Alice doesn't have enough balance, some fees will be reduced from the total balance. This is test number one. However, in the test number two, you will see that even sending 1,000 transactions, our balance is going to keep the same. So no fees is expended. So why this is bad for a validator? Because remember, after adding to the mempool, it's going to send at some point to the execution layer. And every time a validator uses its own resources to compute something or to storage something, it costs money. So if you're able to send transactions and it doesn't cost you anything, attackers can start spamming with transactions to the validator. At the end, it could create a denial of service situation. And the last one, inadequate deserialization, it against affects SUI to the mempool component. It was found through fuzzing. So very quickly, what is SERDI? SERDI is a library for serialization, deserialization in Rust. It's very popular. We have more than 800,000 people using it. OK, this is the structure of a transaction. Here we have the data, the raw data, and the signature. And look at this. This is the happy path. Client have this structure of a transaction, and validator, well, it sends to the validator, and validator has the same structure of the transaction. So everything happens correctly. I'm going to pass this. You see that in this tab, we have the validator. I'm going to run the validator here, and you will see that it continues working. This is the validator. And in the other tab, we have the client. We are going to send this transaction, and it's a published transaction. It's like deploying a contract. It's going to work without any problem, OK, finish correctly, generates a certificate, and if we go back to the validator, everything works as expected, continues working. So happy path, doesn't happen, nothing happened. Second scenario, errors that can be handled. So client now, instead of sending an structure with the expected fields, we are going to add one more field. We are going to put any name, for example, other stuff, with value equals to false. We are going to send that through Tonic to the validator. And remember, the validator doesn't expect the other stuff field. So what is going to happen? Let's see. We're going to run again the validator. This is a validator, and on the other tab, we have the client. So we send it, and appears an error message. This error message is in the client. But if we go back to the validator continues working as expected. OK, if we see the error message, we're going to see that we try to debug that, and we're going to see this. I think doesn't look big enough, but this is macros. And you know that debugging macros is a nightmare. But we have some tools like cargo expand, and at the end, after debugging, we are able to see that the error was raised because the number of the transaction was not found. So we have only 5 different kinds of transactions. OK, it's OK. The validator found it. Finally, we have the same scenario, but instead of putting true, false, we put true. What is going to happen? Let's see. I'm going to go faster. We are going to generate, we're going to make it the validator work again. We're going to send it from the client we're going to deploy the same contract and generates an error message. But if we see the validator stopped working. So we DOS the validator with only one transaction. How many validators are in a blockchain? 20, 100. With 100 transactions, we are able to DOS an entire blockchain, and nothing works. Finally, I'm going to go to the last slide. Some tips. If you can use this mental model of blockchain, it's going to be very useful for this kind of blockchain or others. The best combination is doing manual review, do some fuzzing, and formal verification if it applies. Consider the security of third-party libraries, like in this case, like SERDI, and please deep a lot in how Rust works. I'm talking about concurrency, I'm talking about macros, I'm talking about FFI, etc. And finally, remember that Rust some particular macros to panic the program. So be careful with those. And that's it. Thanks a lot.
Thank you, Louis.